This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
That's right. So if you're matching it up to 50 ohms and essentially the radiation resistance of a dipole is 0.3 of an ohm, what it means is a very small amount of the incident power is actually radiated. Okay? And we also went through the directivity and the radiation pattern. Can anyone tell me what the directivity of a infinitesimal dipole is? Roughly. You can actually tell me in linear units or you can tell me in dB. We calculated it was roughly 1.5, so it's 10 times log of 1.5 is its directivity. Okay, now, and why did we care about studying this infinitesimal dipole? Why did we study the infinitesimal dipole? Well, the reason why we studied it was because there were two reasons. First is if we want to listen to an AM radio station, or we for whatever reason we're constrained and we have to produce a very small dipole relative to the wavelength of the signal that we're trying to transmit. And we went through and showed that, for example, if we had an AM radio station which is transmitting at 1 megahertz, it had a 300 meter which has 300 meter wavelength. If you're trying to include an AM radio station in the form factor of something of this size, you're probably 1,000th of a wavelength, right? And as a consequence, that gave us an indication of how efficient such an antenna is going to be. And what we found out, it wasn't going to be particularly efficient, but the advantages that it had was it's small, right? Then, so that was the first thing. And the second reason why we studied infinitesimal dipoles was it allowed us to develop the machinery in order to be able to analyze more complex structures. And what we did then was we talked about the small dipole, and then we talked about the, these dipoles which are a significantly larger portion of a wavelength. Now, what did we find out about the small dipole? Well, what I'll do is I'll go through this a little bit just as a recap of our lecture. So we worked out this small dipole, we assumed there was a particular current distribution, and that, as I said, is the standing wave pattern of the current on that particular structure. And as I mentioned in the previous lecture, essentially that is, you have to just assume that, or you have to use an electromagnetic simulator in order to be able to calculate that or to be able to determine it. For the purposes of this lecture, or for this lecture course, what we're going to do is we're going to assume this is some kind of God-given fact. Right? So therefore, for a small dipole, what we say is that the current on this structure follows this triangular distribution. And we went through and we calculated the vector magnetic potential, and then I wove my hands and said, look, it's very complex, but here are the electric and magnetic field components for this particular structure. And then after a little bit of mathematics, what we determined was we also determined the radiation resistance for this particular structure, for this, essentially the small dipole. And we found that it was essentially the radiation resistance was 4 times that of a infinitesimal dipole. Okay. Then we said, oh, okay, great. What happens under the circumstances where we now have a dipole which is a significantly larger portion of a wavelength? And we went through, and again, with a little bit of hand waving, because the mathematics gets relatively complex very, very quickly, what I did is just showed you what the electric and magnetic fields are, and also showed you what the radiation intensity for this particular finite length dipole is as a function of its length. And what we showed was that if we had a wavelength which was less than a tenth of a wavelength, its beam width is approximately 90 degrees, a quarter of a wavelength, its beam width is about 87 degrees, and as we get to a portion of a, as we get closer to a full wavelength, we found out that its beam width is approximately 47.8 degrees. Now, when I'm saying beam width, what do I mean here? What was I specifically referring to? Remembering in the context that what we're saying is a dipole is an omnidirectional antenna. So what does that mean? So what does these angles, what do these angles refer to? Sorry? The E-plane. Yeah, the beam width in the E-plane, right? Because the H-plane is essentially a circle, right? And it's also, the other thing that it's also telling us is, as we make these dipoles larger, the beam width goes down, right? What does that mean? In terms of, if I was working out my directivity, if the beam width gets smaller, my directivity gets smaller or larger? Right. Why? What was this magic formula that we went through the process of either calculating the directivity through these complex formulas, but we also had these simple, dirty rule of thumb formulae. Theta 1, theta 2. Okay, so what we did is we had a simple formula relating directivity, which is approximately 41,000 on theta 1, theta 2, which is the angle or the beam width, right? And what we're saying is, well, you can say theta 2 is the beam width in electric field or in the E-plane, and theta 1 is electric field, theta 2 is the magnetic field. Anyway, what we said is the magnetic field, because the dipole is an omnidirectional radiating structure, that's 360 degrees. So the only thing that varies is the donut, or how wide that donut is in the E-plane. So as we make our antenna larger, or a significant portion of the wavelength, what we found is the directivity of this dipole actually goes up, because we've got a 1 on theta type relationship. Okay. Then, just to recap, we also went through and calculated the radiation resistance. Now, because this involves a whole bunch of sine and cosine integrals, and by that I mean cosine on y, sine on y, which are relatively complex integrals to calculate. You have to use Cauchy's integration theorem, but we won't talk about that. Let's assume that you will have these available to you in your in the exam, or if you're working as engineers, you plug it into a tool like Mathematica, or you look up a book of integrals, and you can actually work out the radiation resistance. Now, what was important about this? What did we find? Essentially, what we found was, as the length of the dipole became larger, what happened is that the radiation resistance actually increased and peaked at approximately, say about 170 ohms at about 3/4 of a wavelength. Right? And we also saw that at half a wavelength, the impedance of a dipole is roughly about 73 ohms, or the radiation resistance of a dipole is roughly 73 ohms. And the other thing that this graph actually also showed us is, as we get larger, the dipole actually gets larger, increasing from about 3/4 of a wavelength to about 1.5 wavelengths. The actual input impedance, which is the radiation resistance plus all the other components which are required in order to set up that field, becomes asymptotically larger and tends to infinity, close to about you know, almost like 0.8, 0.9 of a wavelength. Okay? So that just gives us a little bit of information on input impedance, radiation resistance, and directivity. Okay? Now, somebody asked me a question, and I thought it was an excellent question. I thought I would just spend a couple of seconds on it before we start the formal part of this lecture, which is, why do we want directivity? What's the use of directivity? Right? Because there's a trade-off, right? So the more directional an antenna, and I thought a really nice analogy was similar to a hose, right? So you're watering your garden. The more directive an antenna is, you can think of it as you're actually making your hose actually spray water, in this particular case an antenna, in a particular direction. Now, what happens there is you're actually able to get significantly further distance because all the energy, all the water is actually being directed in a particular direction. So you've got the energy and the stream concentrated in a particular orientation or particular direction. So you can get greater distance. But what does it tell you about the area that you're able to cover? Quite small, right? So therefore, if you were using it in one of these devices and it was very highly directional, what it would mean is that you would need to very carefully orientate your antenna or your actual device in order to be able to maintain communications. Right? Whereas if the antenna is less directional, it means it's less spatially constrained. It means you can actually change it and actually change the orientations and be able to maintain. So therefore, you're not as spatially constrained. You're not. You can change the orientation and continue to maintain communications, but at the price of having decreased distance, right? Because you've got less gain, right? And that's the reason why we were looking at directional antennas. Like, for example, if you're at 60 gig and you're, you know, for example, if you're building 60 gig chipsets and you had very highly directional antennas, what you would do is you would need to sit there and try to orientate the antenna at points, you know, if it was highly directional to a particular, to the transmitter or to the receiver. So you just have to sit there and it would be very sensitive. Or what you would need to do is, you know, produce a phased array or something where you can actually point the beam. And we talked about very briefly about phased arrays, and I suggested that, you know, it was something that's very, very cool, and it's something that you should, if you have the opportunity, just to go up and look through the literature to actually understand how they work. Because they're really cool stuff, and you can actually use essentially you're using multiple antennas, changing the phase, the relative phase of the signal that you're feeding each of the antennas, and you can have constructive, destructive interference and use it to point a beam. Okay? So that concludes our foray or our introduction into antennas as part of this course. And now we're going to go back and start discussing transmission lines. Now, I know you've all done transmission lines before, so at least for the first part we're going to go through it relatively quickly, and hopefully you're not, when I'm asking questions, you all don't avoid answering the questions. So the very first question I have for all of you is as follows. When do we use transmission lines? Is it only for, okay. We use transmission lines, okay, when we want to transmit data or transmit information or transmit energy. But when do we need to worry about transmission line effects? So the question specifically that I'm trying to ask is, suppose I've got a DC signal. Do I have to worry about transmission line effects? No. No. Okay. Suppose I've got a battery. Okay, I've got a switch, I've got a transmission line, and I put, at the end of this very long transmission line, I put a resistor or a capacitor. Let's say it's a capacitor, right? So it looks like an open circuit. Right. What happens when I flick that switch? It goes up instantaneously? Suppose it was even a resistor. Would it go up instantaneously? Okay. Because the speed of light tells us how fast the signal can go from one point to the other. And if that transmission line is a significant portion of a wavelength, it takes a finite amount of time to get from one location to the other. Right? So even though you flick the switch in the DC, what you need to worry about is, unless it's perfectly matched, you do get these transients. Therefore, the line's charging up. That disturbance travels across the line. If the impedance isn't matched, and what we'll do is we'll do all these bounce diagrams in 2 lectures' time. You get a reflection, it comes back, hits your generator, and goes back, hits the source again. So therefore, you get this fluctuation in your voltage across the line, across that transmission line. And if you're doing digital design or even analog design, when you flick that switch, essentially what you have is a transient on that system that you need to be able to deal with. And what we'll do, we'll go through in the next couple of slides, next couple of lectures, is how to calculate those transients. But before we do that, what we're going to do is we're going to talk a little bit about more the steady state analysis, which is what we're used to, and where we think of transmission lines as systems which are being used to transmit high frequency signals, right, rather than transients. Right? Now, we've said that transmission lines are this concept of the waveguide, right? So therefore, it's essentially a mechanism or let's think of it as a piece of equipment or something which is able for us to transfer energy. Okay. And usually, the reason why we care and where the effects become more pronounced is when it's a significant portion of the wavelength. Now, if you're at lowish frequencies and the distances are short, you can pretty much neglect a lot of these effects, right? It's usually when you're at a significant portion of a wavelength that these effects become a lot more pronounced. And there's multiple types of wavelengths, these waveguides. Now, on a PCB board, can anyone tell me what some of the predominant transmission lines are called? The transmission lines that you usually make on a PCB board. What would you call them, or what are they usually called? The type, sorry. What type of waveguides do we produce on PCB boards?
Tracks.
They're tracks, but they've got a special name, right? Who's heard of something called a strip line or a microstrip? Okay. So what I'll do, we'll go through it in the next few lectures, but what I'd like for you to do is just quickly at some stage look up look up on the internet or wherever what's a strip line and what's a microstrip, because it's very, very interesting, because that's the type of transmission lines that you're more than likely going to encounter as electrical engineers. Unless, yes, there's people that are also power engineers and they have transmission lines as part of transmitting 50 hertz signals, but generally most of us deal with transmission lines on PCB boards, which are strip lines or microstrips. Okay, so in the previous lectures we talked a little bit about the transfer of energy, and we talked about essentially Maxwell's equations and how the electric and magnetic field was used to transfer energy. Now, what we're doing in transmission lines is essentially the same thing. It's just dressing up Maxwell's equations in a lumped circuit equivalent, right? So we're actually rewriting Maxwell's equations of wave propagation in terms of inductors and capacitors, resistors and conductors. That's all we're doing in transmission lines, right? Now, it might seem like they're completely different things. One, we were talking about Maxwell's equations, and we were talking about div and curl and the like, and electric fields and magnetic fields. And when we're talking about transmission lines, you know, we're always thinking of, you know, inductors, capacitors, resistors, and conductances. Well, we'll start off with this, but what we'll do as part of this lecture actually show what the relationship between, for example, inductance and a B field, right, or the magnetic field. Okay, so let's start off by looking at a very small section of a transmission line. So what we're doing here is looking at, we've got a very large transmission line, and what we're going to do is look at a very, very small segment of this transmission line, and we're going to model this very, very small segment of a transmission line as this equivalent lumped circuit, right? And what we're essentially doing is saying, well, at this little bit, so if we had a large transmission line, you can actually say, well, we're going to take a little segment out here, and this segment is essentially that thing, and we're going to do the modelling on it. And essentially what we're saying is, well, at this interface there's a voltage and there's a current going in. Then of course there's going to be a current leaving and a voltage at the other end of this segment of transmission line. Now, what we're going to say is we're going to model this segment of transmission line as having a little bit of resistance, which is the series resistance per unit length. We're going to say that it has a little bit of inductance, right, which is the inductance per unit length. We're going to say, well, there's going to be loss in this transmission line, and this loss, which is going to be a shunt conductance, and we're also going to have a shunt capacitance. Now, if we were talking about a coax, can anyone tell me what is the cause of this shunt conductance? Does anyone know? Shunt conductance.
Where is it come from?
Yeah. Suppose I had a coax, piece of coax, right? So we're talking about transmission lines, and we know a piece of coax is a transmission line, right? And what I'm saying to you is I've written this equivalence lumped circuit model, and you've probably seen it in the past, and you know your lecturers have just put it up there and said, hey, this is the equivalent model. And you've said, okay, my lecturer has told me that this is the lumped equivalent circuit model. And I'm saying to you, well, why do you believe me? Just because I've written it, I could be completely nuts. I could be a madman, right? So I'm asking you, why do you think, where do these components come from? Or if you had a piece of coax, where do you think some of these components come from? That's right. So that would be the capacitor here. You would have the leakage through the dielectric, right? And that leakage through that dielectric could actually be leakage through air, or it could be leakage through, you know, a particular dielectric material if you're building a coaxial cable. And the resistance is usually the skin resistance of that material, right? And the inductance is the material's ability to stop the instantaneous flow of current, right? So therefore, essentially what happens is whenever you've got a field, whenever you've got current flowing, it usually takes energy in order to be able to change that instantaneous amount of current, and that's what inductance is. Remember that the voltage is L didt, which is actually telling you what inductance is a material's opposition to the change in current. Okay, that's where it all comes from. So it makes sense, right? So even though you might think your lecturers are all nuts and crazy and they're just putting, you know, dumb stuff on the how do you call it, on the you know, on the blackboard, or you know, on their overhead material, there's physical reasons, you know, for this actual model. Now, what we're going to do is use Kirchhoff's voltage law and Kirchhoff's voltage and current laws in order to be able to work out a relationship between the voltage here and the voltage at this location and the current going in to the current leaving. So, can anyone remind me of Kirchhoff's voltage law? Guys, you're final year engineers, so this should be like...
So the voltage across a closed loop is always zero.
Perfect. And current? Current. Yeah, but that's right. But what's Kirchhoff's current law?
It's a dot and the current goes through equals to the current goes away from the dot.
That's right. Perfect. Yes. Current entering has to be the current leaving, right? Because there's conservation of charge, and the voltage around any loop sums to zero. Right? That's both Kirchhoff's voltage and current laws. So essentially, when we rewrite Kirchhoff's voltage law for the voltage, essentially all we're saying is that the voltage here plus the current drop is equal to the voltage here, right? So it's essentially, if you do this, right, that's the relationship for the voltage that you would get between, essentially a relationship between the voltage, the current that's flowing through the resistor and the inductor, and the voltage that you get at the output. Likewise, using Kirchhoff's current law, the current going in is equal to, subtract the current that's going down through this shunt conductance minus the current that's lost through the shunt capacitance is equal to the current that's actually flowing out of this port or out of this node in this equivalent circuit. So that's essentially all I've done here in order to set up the following relationships, which will then give me the differential equations in order to be able to give me the frequency relationship between the voltage and the current on this, on this transmission line. And then what I've done is I've said what's the difference in the voltage as the limit of this small piece of transmission line goes to zero, and what we've got is the change in voltage with respect to distance is just R times the current plus L di dt. Right. And likewise, if I work out, from my relationship for current, what's the variation of current with respect to distance, or the derivative of current with respect to distance, it's G times the voltage plus C dV dt. Okay. And these two relationships that I've got here are essentially what is known as the transmission line equations. Now, in order to be able to make this a little bit simpler for us to solve, I'm going to assume, in this particular case, and this is only for, what I'm doing here is deriving things for a special case, which is for sinusoidal excitation. And what I'll do is I'll re-emphasize this, that all these relationships that I'm deriving are for sinusoidal excitation only, and we'll do the transient analysis of the non-sinusoidal excitation at another time, or the transient analysis at another time. So when I'm talking about sinusoidal excitation, what am I saying? That this is the steady state response, right? When I'm exciting with a sinusoidal type of signal. And all I've done here is I've rewritten, if I say di dt, and I'm assuming everything's sinusoidal because it's a linear system, right? So if you've got any circuit composed of inductors, resistors, capacitors, and shunt conductance elements, we know that it's a linear system. So if we put a sinusoidal signal in, we expect a sinusoidal or cosinusoidal signal out. We only expect an amplitude and phase change. We don't expect to see any harmonics or anything like that. And what we can do is we can rewrite these transmission line equations in phasor form. Right. Now, we need to solve these, right? Now, usually, so what's difficult about solving these equations? Nothing much, but I guess what's important to point out here is that they're coupled. Right? What does coupled mean? When you've got a system of coupled differential equations, what does it mean? It means that the voltage depends on the current and the current depends on voltage. And essentially you can't solve each one of them independently. Right? So you have to solve them as a coupled set of equations. But fortunately here, we can do a little bit of a trick. And usually in order to solve these coupled differential equations, have you all solved coupled differential equations? You must have in your second year maths, right? So where you worked out the eigenvalues to the coupling matrix, and it was e to the eigenvalue, lambda 1, eigenvalue 1, eigenvalue 2, or, depending on the order. Yes? You're nodding. Anyone else? Who's never seen how to solve, who has not solved coupled differential equations before? So the answer is yes, you're just not saying no. Okay, perfect. All right, so the trick here is we've got the relationship of voltage versus distance, or dv dz, and we've also got the I dz. Now we know if we differentiate dv dz by dz again, we'll have d squared v dz, and we'll have di dz here, and we can see that the resistance and the inductance doesn't depend on distance. And likewise, if we do that, we can substitute the second derivative here. We've got the second derivative here, di dz, so therefore we can actually resubstitute di dvz into that part of the equation. So therefore we've got two second order ordinary differential equations, which we learned in first year science degree, or first year whatever, on how to solve. Okay? And if you remember, if you've got a second order differential equation, right, you're able to have e to the gamma or e to the alpha function z, and also e to the, oh yes, no, that's right, sorry. There's a plus here, which I don't have to put the plus in. Okay, so what it says is you've got an e to the minus gamma z term and an e to the positive gamma z term. What's the difference? So then usually, if you've got a second order differential equation, right, and you've got minus gamma squared, if you differentiate twice, that you lose the information about the sign of the gamma. But what does that gamma telling? What's the e to the gamma minus gamma z and e to the positive gamma z telling us? That we've got a solution, one that's moving in the forward direction, and the other one's moving in the reverse direction, right? E to the minus gamma z is essentially the solution to the differential equation, or the second order differential equation that's moving towards positive z's, and e to the gamma z is essentially the solution, which is moving backwards towards towards minus z. Okay? That's just your first year maths. Yes?
Excuse me, we don't have page 3 on our lecture slide.
You don't?
Yeah.
All right, sorry. I will redo it and put it up. Okay, thank you. Can you do me a favour? One of the things that you'll realise about me is I forget really easily. So can you send me an email, or someone send me an email so I don't forget? Because by the time I walk out of this room, I'll forget it. Okay, perfect. And essentially what you'll also find is gamma, which is a propagation constant, has a real component and an imaginary component. And all of it, this gamma is R plus j omega L plus G plus j omega C. Right, now, before we move on, if I said we have a transmission line which was lossless, what would that propagation constant be equal to? All right, so I said this is our propagation constant, and it's written in terms of R, it's written in terms of L, it's written in terms of G, and in terms of C. Right? Resistance, inductance, conductance, capacitance. If it was lossless, if I had a lossless transmission line, what does R equal to? Sorry? There's no R? Yes, that's right. Because R is 0. What else goes to 0? Perfect. All right. So if I'm saying that a transmission line is lossless, essentially what I'm saying to you, if you had an exam question or you were trying to make an approximation for a lossless transmission line, essentially what I'm saying is the R and the G's are 0. Right? Now, in reality, that never exists, but in some cases, it's a good enough approximation. Right? And for exam questions, in order to save you a lot of mathematics, a lot of times it's just like, hey, it's a lossless transmission line, start from there. Okay, so we've calculated the propagation constant, and we've determined what the voltage is, and then also, since we know the voltage and we know that the dV dz is equal to minus this component R plus J omega L I of Z, which we know which can be rewritten as gamma V naught e to the minus gamma plus gamma e to the V naught minus e to the gamma Z. What we can do is now come up with a relationship for the current that's on that transmission line. And furthermore, just for everyone's benefit, what we're going to do is we're going to define a concept called the characteristic impedance of a transmission line. And what the characteristic impedance of a transmission line is R plus J omega L on gamma, and we know that gamma is this quantity. So essentially all we're saying, right, is that the characteristic impedance, and I'm going to get this wrong and embarrass myself immensely, is just this, right? And essentially when R and G is equal to 0, we find that the characteristic impedance of a transmission line is just the square root on L on C. Right? Now, the other thing that we can see from these relationships is that the voltage on the ratio of the positive going voltage wave to the ratio of the positive going current wave is equal to Z naught, but importantly, the ratio of the negative going voltage wave to the negative going current wave is equal to minus Z naught. There's a negative sign there, right? So if you go through your calculations, don't forget this. This is very, very important, right? And usually a place where a lot of students make mistakes. Okay. Now, we've gone through all this and we've worked out what a transmission line looks like, and we've worked out what the propagation constants and the characteristic impedance of a transmission line is. Now, I was talking very briefly at the start about, well, a transmission line is essentially just a reorganization or another way of writing Maxwell's equations. And what I'll do is talk to you or provide you the machinery or the mechanisms, or even at least show you how to relate concepts like electric field and magnetic field to the lumped circuit equivalent elements. Okay, so we know, and we talked about this briefly, that the magnetic field stored, or the average energy stored in the magnetic field, is equal to a mu and on some constant h, essentially the B field squared over a surface, right? And we know from your first year, or maybe second year, that the energy stored in the average energy stored in an inductor is Li squared on 4. That's the average. So therefore, you can actually equate these two. And essentially, what it tells you is, if I gave you the magnetic field, you can actually work out the inductance through this relationship, which is just H star ds. Likewise, we can go through and calculate the energy stored in an electric field. So if you had a coax And, you know, that's the core of the coax. You've got the dielectric material here, and then you've got the outer sheath, which is usually your ground. You can go through the process and calculate the capacitance per unit metre. And likewise, you can actually start working out what the resistive losses is going to be for this particular coaxial cable or transmission line or waveguide. Now, the thing that's important here is when you're working out the loss in the conductor, it's actually the current that's actually flowing, or the magnetic field in this particular case, or, you know, and we know that there's a relationship between magnetic field, displacement current, and actual current, and that's just Maxwell's extension to Ampere's law. And essentially, the loss is, you know, the integral over the inner and outer surface of these two contours, right? And you can actually go through and work out what the resistance equals to the skin resistance over the total current. And likewise, you can actually go through and calculate the shunt conductance. And you can actually go through this and work out what the relationship is. And we did this, we talked about this question at the start, so I won't go into too much, I won't repeat myself, but other than transmission lines are very useful because, you know, they're used in order to transfer energy across a transmission line. Now, sorry, across a surface or between two components. Now, the question, however, is for all of you that have gone through and designed the chip or designed the PCB board, usually you've got an electromagnetic simulator and you've also got a circuit simulator, right? So who's gone through the process of actually designing a component? Not you, Will, don't answer that. That's actually gone through the process of actually designing a circuit or a system? Yeah, you? Okay. So suppose you wanted to know how would you work out what the impedance of a line is or something like that on your PCB board? Or how would you simulate it? You can say, oh, I haven't done it yet. That's why I'm taking this course, right? Okay, so usually what you need to do is you've got either, who knows what an electromagnetic simulator is? Yes? No? Okay, suppose you want to solve Maxwell's equations, right? And we know that if you've got a complex surface, it's really hard to do all this, right? Because you can't sit there by hand working out, you know, if you might have complex structures and, you know, the antennas might look weird and there's transmission lines and the transmission line patterns, the actual metal and the dielectrics, they're really complex structures and you don't know how to deal with them, right? Well, you can't do that with calculations by hand. It's just way too complex. So there are pieces of software which allow you to work out what the characteristics of that structure are going to be, like how much power is going to be radiated, what its input impedance is, what its scattering parameters are going to be, etc., etc., etc. The problem, however, is when you're getting a data sheet and you're like, for example, you're designing a PCB board, you've got a transistor, right? And a transistor isn't well simulated in these electromagnetic packages, right? Because all of those electromagnetic packages are doing solving Maxwell's equations, whereas if you're trying to simulate a transistor or a resistor or something else, what you need is a circuit simulator. Who's used a circuit simulator before? Who's used SPICE? Yep. Right. But it doesn't solve electromagnetic equations for you, right? So essentially, what you do is, for example, if you wanted to, you know, design your PCB and you said, I need a transmission line, well, you can't arbitrarily just use one or the other so in order to do your full design. So essentially what you do is you build a segment of transmission line, and based on all the parameters like the dielectric constant and the loss tangent, and the resistivity of the metal that you're using to build your tracks on your PCB. You put that in your electromagnetic simulator, and it gives you some of the components, like electric and magnetic fields, and characteristic impedance of that piece of transmission line. Right. Then what you do is you use that information in order to come up with an equivalent circuit model. And you put that equivalent circuit model into your circuit simulator. So therefore now you can actually start adding resistors, transistors, in order to be able to design your power amplifier. Right. And then you do your power amplifier design or your amplifier design, and you know that, hey, this is going to work as I expect. Right, and you're also probably going to do your Monte Carlo simulations to actually see, well, if I get process variation or whatever, some kind of variation, this is how it's all going to perform. All right, so I know you're all doing cadence as part of your workshops, right? And at the moment that's an example of a circuit simulator. I haven't given you, I haven't done an electromagnetic simulator. We're not giving you an electromagnetic simulator to use. But you can think of it as, hey, I get an electromagnetic simulator, I work out my equivalent circuit parameters, and I use it to put into my circuit simulator in order to work out if the circuit that I'm building is actually going to meet the required characteristics that I design. Is it going to give me the desired performance at a particular frequency, across process, across whatever? And here I'm actually telling you, essentially the process. You can't usually do co-simulation. You can't usually do, until recently, circuit and electromagnetic simulation at the same time. And usually what you needed to do is go through the process that we've just described, where, hey, I'm going to connect these things up, even if it's on a chip or even if it's on a PCB board. I go through the process and work out what are the equivalent circuit parameters for this electromagnetic or complex waveguide structure that I've got in order to transfer energy between these two components. I work out the equivalent circuit parameters. I put it into a model simulator. I do the design, I work out what it is, I simulate it, I hope that I get the right values. Maybe I need to change them a little bit, then I've got to go back, put them back into the electromagnetic simulator because I might have made the line too big, or I might have needed to make it a little bit wider in order to meet, design rule checks, right? Because you can't make arbitrarily thin transmission lines or, have arbitrary stack-ups. And you go through this iterative process. And that's all I'm trying to show here, that there is a reason why we're working at the equivalent circuit models. Now, let's go through a couple of examples. So the first example that I'm going to talk about is this magical coaxial cable. So who knows what a coaxial cable is? Who doesn't know what a coaxial cable is? Who has not used a coaxial cable? All right, you've all used coaxial cables. Great. So essentially what a coaxial cable is essentially you've got a thin wire which acts as a core. Usually you've got some dielectric, and the core is used to transfer the signal of interest, and you've got an outer ground sheath. Right, and usually they also put plastic around it just to protect it. Now the core in here could be air or it could be some other dielectric material. Okay? Now, what I'm going to say is, for this particular structure, you can go through Maxwell's equations and you can actually convince yourself that the electric field and the magnetic field for a coaxial cable carrying current, that the electric field is given by this relationship and the magnetic field is given by the following relationship. And here what I'm assuming is that I've got an infinitely long coaxial cable and I don't have any reflections, and because it's a coaxial cable without any reflections, the predominant mode of power transfer is something called a transverse electromagnetic wave. And that also tells me that the E and the, if it's transverse electromagnetic wave, we know that the E and the H field are perpendicular to each other, which, if you really think about it, makes a lot of sense, right? Because if you think about this little segment of coaxial cable, it has a voltage. The electric field is going to, the electric field lines are going to go from the center of the core of this coaxial cable to the outer sheath, which is the ground, and also the magnetic field is going to be, by the right-hand rule, circles, which are encapsulate or go around the current carrying core. Now, what all I'm doing here is going through and working out, if you had these two values, can you work out the equivalent circuit parameters? And what you can do is you can go through and show using the formulae that we had derived, or at least being presented in an earlier part of the of this lecture, and you can work out the inductance for this coaxial cable. And if you go through and you say that I'm going to integrate between the surface of the core to the sheath, and I'm going to go over an angle from 0 to 2 pi, you can actually work out for a coaxial cable that its inductance, right, is actually permittivity, and since we don't have any magnetic materials in the area between the core and the outer sheath, you can actually work out its inductance. So it's permeability on 2 pi log of the outer diameter to the diameter of the core. Right? And it's fundamental. You can't do anything more than that. And actually, so if I gave you any coaxial cable, you can actually work out what its inductance is going to be. Right? Likewise, if you're working out its capacitance, right, and you go through the same process, you can actually show that the capacitance for this structure is equal to 2 pi epsilon dash. Does anyone remember what epsilon dash is? Remember when I said epsilon is equal to epsilon dash plus j epsilon, double epsilon? That's the real part of the dielectric constant. Double epsilon was actually the imaginary part, which corresponded to what? Loss. To the loss of the dielectric. That's correct. And if you go through this process, you can actually work out the capacitance per unit length of this for any arbitrary coaxial cable is 2 pi epsilon dash L, the natural log of the ratio of B to A. So it's the ratio of the natural log, it goes as inversely as the natural log of the outer radius, which is the thickness, how far the sheath is from the center to the diameter of the radius of the actual core. Likewise, you can work out the resistance per unit length and the conductance per unit length, right? Now, I apologize. I mean, it looked very good when I was doing this at the time. It looks a bit crazy now that it's on a actually on this piece of paper in front of me. But what I've done for you is actually calculated if you had either a coax, 2 wires, or parallel plates, right? That's inductance. What are the capacitance, resistance, conductance, and inductance is going to be for that system of wires. Right? And it's fundamental. You can't do anything about it. That's what it's going to be. So, for example, if I said to you, you had parallel plates, right? And here I'm neglecting, some fringing effect. So therefore, the capacitance is going to be a little bit larger because you have a little bit fringing around the edges. But let's assume that the width was such that we didn't have any fringing. you know that the capacitance between two parallel plates is dielectric constant width on distance. We know that the resistance is going to be 2 times the skin effective skin resistance on the width. And also, what it says is, if you had a parallel plates, the inductance per unit length is